Hello students, I hope all of you are in good health. I will be continuing the course through this presentation. In the last class we had discussed the economic operation of power systems. In this unit, the last section was left, that was unit commitment and their solution methods. Now I will be discussing the unit commitment problem through this presentation. Now what does the problem of unit commitment means? We can have a look on this diagram which has been shown here. Suppose a loading profile is given where the load has been specified for each hour of the day, and we also have an information about the number of the thermal units which are available. Now to meet out this load demand, which unit should be started, which unit should be stopped, and how much each unit will generate to meet this given load demand at the minimum cost, which we were discussing in this, that is the economic operation of the power system. Now, what does this optimal unit commitment means? Because it is not economical to run all the units all the time. So, to determine which of the units of the plant will operate for a particular load is the problem of the unit commitment. And this problem is important for the thermal plants because for other type of generating plants such as hydro, their operating cost and their startup times are negligible. So, their on-off status is not important. So to determine unit commitment or to solve the unit commitment problem means that we are interested in determining optimally the schedule of the available generating units to meet an expected load demand and provide a specified margin of the operating reserve over a specific period of time. To commit a generating unit is to turn it on and to synchronize it to the system so that it can deliver power to the network. Now the problem with the committing units is to leaving them online, considering the economics also, because if the only those units will be committed which will be cheaper, then there will be a lot of saving of the money. And we can decommit those units which are not needed. Decommit means we can turn off those units which are not needed to meet the specified load demand for a given period of time. Now because the load is varying continuously with time, so there is a need to calculate the optimum combination of units over the given period of time. Now to determine which unit of a plant should operate for a given load is the problem of the unit commitment. In power systems, there may be sudden increase of load or fault on the system or fault on the generator, or some generator is shut down for maintenance. In such situations, some system capacity has to be kept as reserve, known as spinning reserve, to meet the unexpected increase in the load demand and to ensure the power supply in the event of any generator outage. So the spinning reserve we can say is the extra generating capacity which is available with each of the generators which are already connected to the power system, and it is a term which will be used to describe the system reserve generation capacity, denoted as SR, and it's the amount of the generation available from all the units synchronized, that is also known as spinning, on the system minus the present load and the losses being supplied. So this is the formula that we can use to calculate the spinning reserve capacity available with the power system. Now the spinning reserve must be adequately carried so the loss of one or more units does not cause too far a drop in the system frequency, and also the reserve capacity requirements are done in such a way that they obey the certain rules, especially which are set by the regional reliability councils. The typical rules to calculate the spinning reserve for a given system is SR is greater than equal to the largest loaded unit, or it may be calculated by SR equal to greater than equal to a given percentage of the forecasted peak demand. The meaning of extra margin or extra generation capacity available means, suppose a generating unit which is supplying a given load and is already connected into the network. Suppose its maximum capacity is 100 megawatt and it is currently supplying a load of 90 megawatt. So we have the difference of 10 megawatts available with this particular unit, means the margin or the extra generation capacity of 10 megawatt is available with this particular generating unit. Similarly, for all the units which are supplying a given particular load demand, they are not running on their maximum capacities, rather they have some margin available with them. And this margin can be calculated in total to know what is the total spinning reserve capacity available with the system. And this is particularly important in case there is an increase in the demand. This extra margin or the reserve which is available, which will be fed to the network to meet the next or the new load demand. The thermal generator usually has some constraint associated with it. It requires an uptime of several hours to bring the boiler temperature and the turbine speed up to the full operational condition before it can be synchronized and brought online. There are some terminologies associated with the time when the unit can be brought to the on state is the minimum uptime. That is, once the unit is running, it should not be turned off immediately. Once it is committed, it has to be in the system for a specified minimum uptime. Then there is a minimum downtime also associated with the thermal units. That is, once the unit is decommitted, that is in the off state, there is a minimum time before it can be recommitted or brought to the on state. It cannot be turned on immediately. It will remain decommitted for a specified minimum downtime. The other constraints which are associated with the thermal units are the crew constraints. That is, if a plant consists of two or more units, they cannot be turned on at the same time because there are not enough crew members or the personnels to attend both the units while starting up. The next constraint is associated with the cost, that is called the startup cost, and it is the cost which is required to bring a thermal unit online. The startup cost can be different from maximum cold start value to a much smaller value if the unit is already close to the operating temperature. That is, if it is turned off recently and still close to the operating temperature. Now there are two terms which are connected with the thermal unit, that is called the hot startup and the cold startup. If the hot startup means that the unit is close to the operating temperature and it has been recently brought to the off state, and the PG is 0, that is we are not supplying any power output from it, but it is still close to the operating temperature, and the generator means the generator is on, and it can be used for a spinning reserve or the hot reserve to take the load due to loss of any unit. And the cold startup means that the unit has been brought to the off state and there is no output equal from that particular unit, means the generator is off. In unit commitment, we create a combination or the possible states of those units which has to be kept in the on state or which will be used to supply the load. The combinations are usually written in the binary form. Suppose that there is an unit system, then the total possible combination or the states will be 2 to the power n. For example, if it is a 3 unit system, then the possible combinations or the states will be 2 to the power 3, that is 8. And here we can see that these are the different possible combinations which has been written there, where 1 means the unit is in the on state and 0 means the unit is in the off state. So we'll be having total 2 to the power n, that is total 8 combinations for 3 unit systems as shown here. Now we'll be discussing the different unit commitment solution methods. The unit commitment problem can be outlined as if there are n units to commit a given load and to dispatch the m load levels, then the total number of combinations will be 2 to the power n minus 1 whole to the power m. In the last slide, we have already discussed that if there are n unit system is there, then the possible combination will be 2 to the power n. But in addition to that, we may have the different loading schedules. For example, for a 24-hour day, we may have the hourly load variations. Then to include that hourly load variations, the combinations will be written as 2 to the power n minus 1 whole to the power m. And we can easily see here that if the number of units are large, or if the loading levels which are given for the hourly or whatever our combinations given, then this number will be very large. So we need some methods to solve this unit commitment problem. The first method is the priority method. In this method, what we do is we list all the combination of units in on state and off state and calculate the total cost of the units which are being committed there, and accordingly a decision is taken to rank those units which are having the minimum average production cost. So the unit which will be having the minimum average production cost will be loaded first, followed by the next. So a ranking order or a priority order is created. To calculate the average production cost of the unit, we can divide the generation cost function of that unit by its real power output, defined as mu, which is known as the average production cost of the unit. Also, we know that the incremental rate of the unit is defined by lambda equal to the rate of change of the cost function divided by the rate of change of its generation. So when the average production cost of the unit, that is mu, is equal to the incremental rate of the unit, that is lambda, then the corresponding average production cost will be called the minimum average production cost, defined as mu minimum. Generally, the power output is close to rated power when the unit is at its minimum average production cost. In the next slide, we'll be taking an example on this, how to create the priority list and how to calculate the average production cost of each of the units. In this example, the 5 generating units are given and their minimum average production cost is also given. So the table 7.1, we can see that the data for the 5 units is given and their minimum production cost mu minimum is also specified. And the minimum and maximum megawatt is specified for each of the units as shown in the table 7.1. Now we want to create a priority list out of this table 7.1. To create a priority list of this, we need to know that the priority will be given to that unit, or that unit will be loaded first, which is having the minimum average production cost mu minimum. So if we look at the table 7.1, we can create a priority order as shown in the table 7.2 as 1, 2, 3, 4 and 5 in the column 1. So in the column 2 we have written that the unit G4. So G4 is having the minimum average production cost of 8.90, right? And followed by the second unit, which is the unit G2. Then the unit priority order third means the unit G1 and then G3 and G5. So this is the priority ordering or the ranking of the units that has been done here. That is, the unit number 4 will be loaded first for given load demand, and then the next unit that will become taking up the load will be the generator 2, then the generator 1, generator 3 and generator 5 in that order, or the priority order or the ranking that has been created here. Let us take one more example. Now in this example, the data for 3 units in a plant has been given, the maximum capacity of the 3 units is defined and their cost function is also given. Now we want to create a priority list for this. To create a priority list, we need to calculate the full load average production cost for each of the unit, and the formula that we have discussed in the last slide is we want to calculate basically mu. So to calculate the value of mu, we need to write first, the formula was, you have to write the cost function and divide it by the power output of that particular generator. For example, for the unit number 1, we are writing the cost function of the unit. In place of P1, we are writing 600 megawatts. So this gives us 97.922 for the unit number 1, which is known as mu, and this is also known as full load average production cost for the unit number 1. Similarly, we will be calculating for the other 2 units. Based on the full load average production cost calculated for each of the 3 units, now we'll be creating the priority list as discussed in the next slide. Based on the calculation of average production cost, now we can order the 3 units and we can create a priority list for the 3 units. Now as the cost obtained for the unit number 2 was least, so it will be given the priority 1. The priority 2 will be given to the unit number 1, which is having the average production cost of 97.922, and the last priority will be given to the unit number 3, which is having the highest production cost. And the maximum capacity of all the 3 units is also written here. Now, if you look at the lower side, suppose the loading combination is also given to us, and suppose the load is lying between 1000 megawatts to 1200 megawatts. So with this load demand, we can see that we need to load all the three units. So how the units will be loaded? The combination that has been written is 2 plus 1 plus 3, meaning that first the unit number 2 will be loaded, followed by unit number 1, followed by unit number 3. So in that order, the load will be supplied. In the suppose the load demand is between 400 megawatt and 1000 megawatt, then only two units are sufficient, that is the unit number 2 and the unit number 1. In the order that unit number 2 will be loaded first and then the unit number 1. Suppose the load demand is less than 400 megawatt, then we require only one unit, that is the unit number 2. And the unit number 2 is sufficient to meet out this load demand of 400 megawatts because its maximum capacity is also 400 megawatt. In this example, four generators are given and the minimum and maximum power output of each of the generators is also specified, and the cost function is given by the quadratic formula with the cost coefficient also specified. We have to calculate the full load average production cost of each of the generator, and we have to prepare a priority list for the generator loading. Also in this question, the loading pattern is given, which we'll be showing in the next slide. The load curve is given for 8 hours. An hourly load profile is given and the different loading demand has been given corresponding to each of the hour. Also the spinning reserve is also specified in the question, which is set to the 10% of total generation megawatt capacity online. Means it has been calculated as SR is greater than equal to the given percentage of forecasted load demand. In this question, you have to set spinning reserve as 10% of the total generation megawatt capacity online. The next data which is given in the question is minimum downtime of the units. So for downtime has been specified for all the 4 units in hours. Means the unit number 1 is down for the 4 hours. Means it can't be brought on the on state before 4 hours if it has been shut off. So in this question now we will be determining the full unit commitment schedule for the system. Now to calculate the full load average production cost known as mu, we will be calculating for each of the unit, that is written as or calculated as we write the cost function of that particular unit divided by the power output of that unit. So here we are writing for the G1, we are writing the cost function of that unit defined by C1 and where the power P1 is 500 megawatt divided by 500 to get a value of $18 per megawatt hour, which is mu, also known as full load average production cost. This is how we will be calculating for all the 4 units. Now once the average production cost has been calculated for all the 4 units, now we can create a priority list as shown in the second part downside. Unit number 1, 2, 3, 4, we have written the full load production average cost as dollar per megawatt hour. As for the unit number 1, it is 18, for unit number 2 is 26, unit number 3 is 22 and unit number 4 is 30. Now how to give the priority is, we'll be looking at the unit which is having the minimum full load average production cost, which is with the unit number 1 currently. So we'll be giving this unit number 1 as a priority 1 or the rank 1. Then the rank 2 will be given to the unit number 3 and priority 3 or the rank 3 will be given to the unit number 2 and the priority 4 or the rank 4 to the unit number 4. So this is the priority order that has been created. Similarly, we can make here the combination of the merit order loading scheme in terms of what load has been connected to the system or what load needs to be supplied. So we may have different combinations here. The first combination is if the load demand is higher than and we need if we require all the 4 units, then the combination will be 1 plus 3 plus 2 plus 4, means the unit number 1 will be loaded first, followed by unit number 3, then unit number 2 and then unit number 4. Here minimum megawatt and the maximum megawatt has been calculated as the sum of their minimum and maximum capacities. For example, minimum megawatt for the first combination is written as 400, means all the 4 units is having the minimum megawatt of 100, so that makes a total of 400. Similarly, maximum megawatt of each of the unit is 500 and for the 4 units it will be 2000 megawatt, like that. Now we are making the full unit commitment schedule for all the loading combination which is given in the it was given in the graph, and here a table has been created with each hour what was the loading combination that has been written here. The load has been specified from the hour number 1, 2, 3 up to 8, and the load that was written there was for the hour number 1, it was written first hour the load was 1600 megawatt. Now in the next table that we are calculating is load plus SR, that is for at any given time the load plus SR will be calculated. That is the load was 1600 and the spinning reserve is 10% of the maximum load or the forecast peak demand we can say. So we are calculating 10% of 1600, that is 160, plus the load, that is 1600. So that gives 1760. Now this is the total load which has to be met out at the hour 1, that is 1760. Now to meet out 1760, we need all the 4 units to be kept online. In the hour 2, the load demand was 1400, and if a spinning reserve is added to it, it will be 1540. So with 1540, we have again found that we need to have the combination of all the 4 units. So like that, the combination of all the units has been written for all the hours. Now before writing this unit schedule, which has been shown in the column number 4, we can just make a binary combination of all the 4 units because the 4 units are there. So total number of combinations will be 2 to the power n, that is 2 to the power 4. So if we calculate 2 to the power 4, combinations will be 16. So out of the 16 combination we are writing here, let's have a look at the combination table. So combination that we have created is 2 to power n combination, that is 16 combinations starting from 0 to 15. So the combinations will be written in binary form as 0, 1 format, and because the number of units are 4, so in the column 2 we have written 1, 2, 3, 4, that denotes the unit numbers, where the 0 written below that particular unit number denotes that the unit is in the off state. If 1 is written below any of the unit, then that means that particular unit is in the on state. In the next 2 columns, minimum and maximum capacities of the units has been written, and in the last column the total load that can be supplied from these of the units has been written. So we'll look again with the combination number 0, which is written there 0, 0, 0, means all the 4 units are in the off state, so no load can be supplied. So we can call this combination as a not feasible combination to meet out the load. In the next case we have written 0001. So 0001 means only the unit number 4 is in the on state, and this combination is also not feasible because the maximum capacity is 500. And if we look at the loading which has been calculated in the above table where load plus SR is written, we can see that we don't have any combination which is having 500 megawatt of load. So this is also not feasible. Means, or we can say in otherwise, we can say that unit number 4 won't be able to supply if the load demand is greater than 500 megawatt. Then the next combination also is not feasible. Then the combination number 3, which has been written as 0011. So we have the minimum is 200, maximum is 1000. So if we look at the load plus SR combination, we can say that the load plus SR combination wherever it is less than 1000 can be met out by this combination where the unit number 3 and the unit number 4 can be kept on the on state. Okay, 1 indicates that unit number 3 is in on state, unit number 4 is in on state, and the total capacity of both the unit is maximum capacity is 1000 megawatt, and they both of them can supply a load demand easily of 880 megawatts. The bracket in which I have written cross, I'll explain this later on. Then next combination again is not feasible because the maximum is only 500 and we don't have such a less load demand in the table. Next is 1000 means 880 load demand at the hour 4 and 5 can be met out. Similarly, in the next In the seventh combination, where we have written 0, 1, 1, 1 means unit number 2, 3, 4 are in the on state, and the maximum is 1500 megawatt capacity. So with the 1500 megawatt means if whenever the load demand, load plus SR, we have to see whenever it is lesser than 1500 megawatt will be easily made out by this combination. So such a combination we are getting at 1320 in the above table. So in the next is not feasible, then this is how we have created up to the last. Now let us come at the last combination, which is 15th combination, which means that 15, the binary conversion of 15 is 1111, and the maximum out of all the 4 units means all the 4 units are in the on state, and the total maximum of all the 4 units is 2000 megawatt. Now with the 2000 megawatt with all the 4 units at the on state, we can meet out a load demand of load plus SR of 1760 can be meet out by this combination plus 1540 combination wherever it is occurring. So in the 15th combination, the feasibility is that 1760 and 1540 load demands can be meet out, and this requires that all the 4 units should be kept in the on state. Now for the 14th combination, we have written 1320 will be meet out by this combination. Now, for some of the combinations where the cross has been put, the cross has been put that although the load demand can be meet out, but we have put here cross because we have to see their downtime also. So, which is specified in the question, the shutdown time for the unit is also given. So, in the combination number 3, if we see that the total load demand 880 we have written, but still we have written cross because in number 3 and 4 we have to look at the shutdown time of these two units, and the shutdown time of these two units is there, that indicates that these units won't be able to meet out the demand of 880 megawatts. The rule has been written here that this is the summary of the steps of the priority list method. The other method that we'll be discussing is the dynamic programming method, which I'll take in the next presentation.